Okay, we're back to the mathematics. Share my screen, the entire thing, and here we go. So today I'm going to begin with discrete relations. Discrete relations. Okay, and first issue is that I do not have my trackpad, or rather my writing pad plugged in. Okay, it's plugged in now, but when you do that, you have to sort of like reset things. Great start to the show. Open it up. Make it big, and we're in. Okay. It opens up with each set of ordered pairs represents a relation. Represent the relation as a table. So, what this means is that -7 is related to 7. But that does not mean that 7 is related to -7. That does not mean that. Just a second. We're just going to wait for the siren to pass because I can't concentrate when a siren is going off. Great. Right. So, okay, so first thing is, let's bring it down to earth. Imagine that you have a collection of father-son relationships, okay? So like, let's say Jack has a son called John and a son called Michael. And then John has a son called Gary. Messing up spellings here. I'll just use my name. John has a son called Josh. And then separate to these, Harry has a son called Max. Okay, how would I represent all of that information using what they're doing here with ordered pairs in sets? Family 1 is right there in the pink. Family 2 is over here in the orange. So what I do is I open up a pair of set braces, learn how to draw that symbol, to write that symbol, I mean. Now, my first entry will be Jack, John. Jack, John. Because Jack is the father of John, my next entry will be Jack, Michael. And then my next entry will be John, Josh. And lastly, I will enter Harry, Max. Okay, all the information is captured there. Notice that John, Jack is not in there because John is not the father of Jack. John is not the father of Jack. And so, you know, it's tempting to say, oh, Jack is related to John. That means John is related to Jack because of how, like, the English, you know, just everyday English language works. But in mathematics, when we say, you know, X is related to Y, and we use this like symbol here with a fancy R, when we say X is related to Y, that does not necessarily mean that Y is related to X. Not necessarily. Okay? Anyhow, let's get started with the actual question. So, how to represent this relation here as a table? What we do is we do a pair of columns. Left X and on the right you do y. And then you think about, x stands for the first thing in an ordered pair, the first entry in an ordered pair. So -7, -6, -1, 1, and 6. That's what I put in here. -7, -6, -1, 1, and 6. And what about over here on the right? You just put the corresponding y value, which is the second entry in an ordered pair. So I put 7, -5, 7, -2, and -5, like that. 7, -5, 7, -2, and -5. And really, to make it a proper table, you've got to do a bit of this. Put in the separators like that. And if I wanted to make it a real table, I would put in a border. But for most people, it's actually, totally fine if you do that. So let's check if that's right. It is. Great. So quite simple, really. Over here, on the x column, we're going to put -6, -6, -7, -6, -6 again, -2, and then -1. And in the y column, we're going to put 6, 5, 0, 3, 1. Hold on a minute. Couldn't I package these up in one row, right? Couldn't I just write -6 and then have the line in the table going down the middle, and then have 0 and then comma 5 like that? Well, you could, but everyone has to agree that that's what that means. That's really what has to happen. And if you're talking to a computer, maybe it won't know what that means. Try entering it into your favorite piece of software and see if it works. Doesn't necessarily work. Okay. Next up. Each set of ordered pairs represents a relation. Represent the relation as a graph. So the word graph, I think it comes from Greek, and it quite literally means writing, like to write. So yeah, that's why they say this, like it's something that you can see that has been written down. That's usually what that means in maths. Anyway, so -4, -5. We go back by -4. Sorry, we go back by 4, which is here, and then down by 5. So that's going to be here. Then 3, -4. Okay, so I go to the right by 3 and down by 4. There. 4, 4. Okay, to the right by 4 and up by 4. 5, 3. To the right by 5 and up by 3. And 5, 7. Okay, to the right by 5 and up by 7. So, is there any clear pattern here? I mean, it looks sort of like an asterism. By the way, when you have a group of stars in the sky, that's called an asterism. A constellation, to my understanding, refers to a specific patch in the sky, and there are 88 constellations, as far as I know. Right? Okay, but is there any clear... doesn't appear to be. Maybe we have an insufficient amount of points for the relation. But anyhow, we have to get on with the show. So, next up, -1, -3. Okay, back by 1, down by 3. There. 0, 6. 0 to the right and up by 6. 4, -5. this next. So 4 to the right and down by 5. 4 to the right and 1, 2, 3, 4, 5. That's going down by 5. I better do these in blue as well, otherwise it confuses. Next, 5, 7. So along by 5 to the right and up by 7. There. Finally, 6, -7. So 6 to the right and down by 7. There. That's fine. That's representing the relations as a graph, each of them as a graph. Here, for these discrete relations, we have to represent them as a mapping diagram. What the heck does that mean? Well, what that means is you have a set on the left, like consisting of your x values, and then a set on the right, which will consist of your y values. Okay, I'm going to show you how to do it. -5 is related to -7. All right. So I put -5 there, -7 over there, and then I put a nice arrow joining them up like that. Okay, so -4, 0 is next. 0, 7 is third. 1, 2 is fourth. And 2, 1 is fifth. Here, sometimes, like, is X the official name? Well, no, the official name is the domain. That's the set of everything that is in the first entry in the ordered pairs of our relations. This set is called the range. The range. Now, I'm going to make sure that this actually follows the house style, as in it's actually what they want. So, checking it out, it appears to be fine. Hold on, what's this crisscross business? Okay, can you see what's happening? It looks like they've ordered the domain and ordered the range, and then the arrows sort of just line up as they should. So we'll do that in the next one then. Okay, domain. Well, we have -4, -1, 1, 6, and 6. All right, so that's fine. That's already in order for us. -4, -1, -4, -1. Then comes 1, and 6 features twice, but we only write it once. So I'm going to write 1, 6, just there like that. Now, what about the range? Let's see. It says 2, -4, 1, 6, -3. Let me put that in order, starting from the least of the numbers. So, -4, that's done. -3, next. 1, 2, 6, after. Now, to create the mapping, -4 maps to 2. -1 maps to -4. 1 maps to 1. 6 maps to 6, but also 6 maps to -3. And that complies with the house style, I believe. Here it says each graph represents a relation. Represent the relation as a table, and then a set of ordered pairs, and then a mapping diagram, and then determine the domain or / range, and if the relation is a function. So, what's the logical order to do this in? It's quite a lot of work, actually, for this one. First, we'll just represent the relation as a set of ordered pairs, which is what a relation actually is. Okay, so how to gather up these points? These three first, in this quadrant over here, which is the second quadrant. Make sure you know that. First, second, third, and fourth. That's the name of the quadrants. So we start on the top right, where most of the action happens. That's why that's called the first quadrant. And then we go counterclockwise or anti-clockwise. And yes, they do have Roman numerals as their names. So anyway, what's this point here? -5,6. And this one, -3,5. And this one, -1,2. Quadrant 4, these 3 points. What's this one? 1, -6. Next, 6, -3. And last, 7, -1. As a table, it's pretty obvious what you have to do. Just do what we did before. X and Y, just there like that. And just literally copy it out. -5, -3, -1, 1, 6, 7, 6, 5, 2. Then comes -6, -3, and -1. Literally, I'm just going the first in the ordered pairs and then the second in the ordered pairs. But as we know by now, the mapping diagram has different requirements. So you have to say domain like that. And you have to actually put the numbers in order. Now over here, conveniently, they actually are already in order. So I just copy it out. As for the range, not so much. It's not in order. So I have to order it. So I do that from the least number to the greatest number. So I'm going to have -6, -3, -1, and then 256. Fun fact, 256 is 16 squared, which is 2 to the 8. Great. Now, to create the map, to create the arrows in the mapping diagram, -5 maps to 6. -3 maps to 5. -1 maps to 2. 1 maps to -6. 6 maps to -3. And 7 maps to -1. Clearly, the graph is sort of like more useful. I mean, you could see that, hey, there's something going on here. Look, these arrows go down and these arrows go up. This group goes down, this group goes up. But by graphing it, we can sort of see the two quadrants filled, and it seems to be a bit better. What was the other requirement of the question? Determine the domain and range. We did. And if the relation is a function. What's a function? A function, officially, is a type of relation. It's a type of relation. Now, a function takes an input and gives exactly one output. So, like, you can't be a function if, okay, in this case, the relationship is one-to-one. One-to-one. There's no like doubles, you know what I mean? But how can I explain that better? The way to explain it better is to say that you can't have two arrows coming out of the departure point here in the domain, because a function gives exactly one output. In addition to that, every single entry in the domain has to have an output. So, I mean, the technical language for that is it's a left total relation, which means that the left set totally has arrows coming out of it. That's how I think of it. But it only has one arrow per entry. Great. And now for this over here. Okay, we're going to gather our ordered pairs. This one first. That's -4, 0. The first quadrant next. 1, 7, followed by 2, 1. Great. The fourth quadrant next. 1, -7, followed by 4, -5. Then 5, -7. And close up your set there like that. The XY table, tabulating the ordered pairs. Look at that. That's the verb form of table. To put in a table, to tabulate these ordered pairs. Okay. As said before, we can literally just peel them off. So -4, 1, 2, 1, 4, 5. And just write them downwards. So -4, 1, 2, 1, 4, 5. Then the second entries in the ordered pairs. So 0, 7, 1, -7, -5, -7. 0, 7, 1, -7, -5, -7. Great. Domain and range time. Oh, wait, I forgot to say. This is it is a function. Okay. Domain time over here. Are these in order? No, they're not. So we have to put them in order. -4 at the top. Then comes 1. Then 1 again? No. 1 only once. 1 only once. The domain is a set, and every single element of a set has to be unique. Okay, so -4, then comes 1, then comes 2, then 4, then 5. And over here on the right, the range. Who features in the range? These numbers, are they in order? No, they're not. So we have to put them in order. -7 is the least. It occurs twice, but we only write it once. Then -5. Then 0. Then 1. Then 7. Now create the arrows in the mapping diagram. -4 maps to 0. That's the first entry, sorted. 1 maps to 7. 2 maps to 1. 1 maps to -7. 4 maps to -5. And 5 maps to -7. Is this a function? No. Because look, the 1 has, the 1 maps onto -7 and +7, which is disallowed. It's not allowed. That's not a function. But it's okay that it's okay that 1 maps to -7 and 5 maps to -7. That's allowed. For something in the range, you're allowed to have many things that map onto it. But for an entry in the domain, you're only allowed to map onto one thing. So let's check and see if they agree. Good. They agree. All right. Oh, it looks like they wanted the domain and range stated as a pair of sets, but it's very easy to do that. I mean, you can literally just read it off the domain range sort of visualization there. So this here is done. So we'll move on to the next thing, which is evaluating and graphing functions. Let's see what that's all about. Okay, we have a bunch of functions here, and we have to evaluate each of them for the given value. So for this first one, the function is 4x plus 6. What does that mean? That means visualize a kind of machine, a machine which accepts a number and gives a number as an output. And what does it do to the number that it takes as the input? It multiplies it by 4, and then it adds 6 to it. So if I were to input the number 10, then it would output the number 46. 4 times 10 add 6, which is 46. That's me evaluating it for the input value of 10. And now I'm going to evaluate it for the input value of 0. That would be 4 times 0 plus 6, which is 0 plus 6, which is 6. This function here literally just adds 2 to any input that it gets. So if I input the number 7, the output is 9. You may have seen a function visualized kind of like this. Like this is a machine. There's the input. That's where you put the input in. And then like here's the output. The output comes out there. It's my drawing of a machine. And the machine has like F on the outside of it. That's its name, the function machine. And you know, here you get to see what the innards of the machine look like. You take off the casing on the outside and you see the cogs and the various other things inside it and how it transforms the number. Okay, so for this one here, I would like imagine putting in 7 and 9 comes out the other side. You can also kind of, if you think about it, if you were looking down that opening of the machine, it would kind of look like a circle, right? Where you feed in the number. Okay. And for brackets, it's kind of like they have a little bit of the circle missing, you see? So it makes sense that like 7 is going into the chute, and then the equal sign is kind of like the exhaust or whatever you call it coming out of the machine, and so 9 comes out. That's just a funny way that I have of visualizing it. What's going on with this function here? It takes the input, multiplies it by -3, and then takes away 5 from that. And we have to evaluate it at -8/3. So you literally just write out f of -8/3. You put an equal sign, you put your -3, and then where x is, which stands for input, you put in -8/3, but please do so inside a pair multiplied by -8/3. That is 8, and 8 take 5 is 3. Great. Okay, a bit quicker now. A third take away 4, which is 4/3 take away 4, which is 1 1/3 take away 4, which is going to give us a -2 2/3. Here, f of -1.9 equals -4 times -1.9, take away 1. And what's -4 times -1.9? Well, that would be 7.6. And 7.6 take away 1 is 6.6. Great. Input -1.6 into this function here. This is kind of a function, by the way, very common. It's called a linear function. You know, what it's asking you to do is multiply the input by a number and then add a number to it. So here's like the generic or general form of a linear function. They all basically look like this. Multiply your input by a number and then add a number to that result. Indeed, A may stand for 1 and B may stand for 0. That's the function that effectively just does nothing to a number. It's a machine that's empty on the inside. You put in the input and out comes the output. Okay, but in this case, f of -1.6, that's 4 times -1.6, and then take away 1. So -6.4 take away 1 is -7.4. Great. Here we have a solid pair of bars on the outside. What does that mean? That means the absolute value of whatever is on the inside of the bars. And what's the absolute value of something? It's when you force something to be positive. Okay? So the absolute value of -7 is 7, and the absolute value of 7 itself is just 7 again, because 7 is already positive, and the absolute value of 0 is 0. Okay, so you stick in -6 where x is. If you don't know what to do, just do this. Minus sign, the bar of the absolute value, then -6 where x is, then take away 1, then the closing bar, and then 5. You'll get points for this, just showing that you can substitute correctly, right? And remember, if in doubt, bracket your substitution. If you think the minus sign is going to cause trouble, just bracket it. It's fine. Okay. Minus 6 minus 1, that's minus 7. So minus sign, the absolute value bars on the outside, and minus 7 on the inside right now. Now, what's the absolute value of negative 7? Well, that would be 7. And then we've got a minus sign in front of that. So it becomes negative 7. So negative 7 add 5 is negative 2. Great. Now we understand how that works. What's the absolute value of 6 add 5? Well, that would just be 11. And what's 11 take 2? Well, that would be 9. So f of 6 equals 9. 2 more. This here is called a quadratic function. A quadratic function. We're going to input negative 2 and see what it evaluates to. We square negative 2 first to get 4, but the minus sign in front makes it minus 4. We times negative 2 by 8 to get negative 16, but the minus sign in front makes it positive 16. And then we take away 12. Negative 4 add 16 is 12, and 12 take 12 is 0. So f of negative 2 is 0. Similar story over here. Input negative 4 where x is. So square negative 4. What do we get? 16. But there's a minus sign in front, so it becomes minus 16. Multiply negative 4 by 8. What do we get? Negative 32. But there's a minus sign in front, so it becomes positive 32. And then take away 13. So f of negative 4 is this computation here, which is 16 take 13, which is 3. We have to graph each function for the given domain. So the domain here is negative 5, negative 4, negative 3, negative 1, and 2. So in other words, you've got to stick in all these numbers to get the outputs. We'll just do it one at a time. If I stick in negative 5 in there, I'm going to get negative 10 add 2, which is negative 8. So I go along by 5 to the left and then down by 8. There. Just there like that. Handled. Next up, 2 times negative 4, which is negative 8, and then add 2 to that, which is negative 6. So we go negative 4, negative 6. Just there like that. Handled. Next up, negative 3. 2 by negative 3 is negative 6. Negative 6 add 2 is negative 4. So there we go. You can see this is forming a straight line. These 3 dots here are known as collinear. It means they lie in a straight line. In general, a linear function does form a straight line. But I don't want you to get ahead of yourself and just start putting in dots like that. That's wrong. We have to just do the entries that we're told. So negative 1 goes in next. 2 times negative 1 is negative 2. Negative 2 add 2 is 0. There. 2 is last. 2 times 2 is 4, and 4 add 2 is 6. So 2 to the right, 6 up. But wait, am I supposed to connect up the points? Wait, did I do that right? Ugh, beg your pardon. When you take stuff slower than you used to, sometimes you make mistakes. Do you know what I mean? Like if someone told you to walk in slow motion. Okay, so when I put in -1, I get -2, and then I have to add 2 to it, so I get 0. So it should really go here. As for 2, well, that actually does go to 6. So there. So don't connect up these points in a straight line. You're not asked to do that. They're just asking you to graph each function for the given domain. It's not necessarily true that a function has to include every single number. It doesn't have to. Okay, so in the domain. So next up, the domain is just 0, 2, 3, 4, 5. So we just stick those in, and let's do that now. All right, so I'll just write the numbers here like in a straight line. So 4, then 0, then -2, then -4, then -6. Okay, so it should look like 0, 4, there, 2, 0, there, -2, beg your pardon, 3, -2, 3 to the right, 2 down, there. 4, -4, so 4 to the right, 4 down, there. 5, -6, so 5 to the right, 6 down, there. And it lies, all these points lie on a straight line. And we already know ahead of time that a linear function's dots or points look like that. So this helps you check. Okay, we've got the absolute value here. So -8 add 3 is -5. The absolute value of that is 5, and 2 times 5 is 10, and 10 take 5 is 5. So -8 to the left and 5 up, like that. Then I stick in -5. -5 add 3 is -2. -2 absolute value is 2. 2 times 2 is 4, and 4 take 5 is -1. So we go -5 to the left and -1 down. There, like that. Stick in -4. -4 add 3 is -1. Absolute is 1. 2 times 1 is 2, and then 2 take 5 is -3. So -4, -3. Like that. Stick in 0. So it becomes just 2 times 3. And 2 times 3 take 5 is 1. So we have 0, 1. Stick in 3. 3 add 3 is 6. 6 times 2 is 12. 12 take 5 is 7. So 3 and 7. Okay, so for the absolute value function, when you do like a linear version like this, it feels linear, right? It's going to basically look like that somehow, like a V. And we can sort of see that, roughly speaking, there. So that checks out. For a quadratic function like this, it's going to look like a U shape. Official name for it, parabola. Parabola. That doesn't help you so much here, but anyway. So we're going to stick in -4 and see what we get. So it's 16 take 8, which is 8. So it's 1 take 2, which is minus 1. So it's 0. So it's 3. So it's 4 and 4 is 8. Great. And then you just plot them. So minus 4, 8. That will be here. Great. Negative 1, negative 1. So I'm going to go there. 0, 0, there. 1, 3, like there. And 2, 8. So there. Great. And we can sort of see the U shape, the parabola rather. Now we have to graph each function. So that literally means plot an infinite number of little points. You know, no problem. I have an infinite amount of time. So not really. So this first one is negative 3x takes 6. So it's good to be able to like read this kind of linear function. So I know, because there's a minus sign there, that it's going to slope down from top left to bottom right. I know that because it's minus 3 and not something like minus 2 or minus 1, I know it's going to be really steep like that. And then because there's minus 6 there, I know that it's going to pass through minus 6 there like that. That's just an ability you need to develop when you see a linear function, just to mentally graph it quickly in your mind. But anyway, to really graph this, you just need 2 points, because 2 points completely define and pin down a line, right? So we have 1 point already where it crosses the y-axis. What's the next point going to be? Oh, where it crosses the x-axis? You can do, but why give yourself a headache? Just put in like 1. Just put in 1 and see what happens. Okay, so I put in 1 and I get negative 3 takes 6, which is negative 9, which is off the page. Okay, fine. I'll put in minus 1. I put in minus 1 and I have 3 takes 6, which is minus 3. So 1 minus 3. Minus 1 minus 3. 1 to the left, 3 down. And there you go. You just need those 2 points there. Then get your ruler. Now, I don't know if this thing actually has a ruler in it, but I'm going to see. Oh, it does. Amazing. Okay. Maybe not so amazing. Okay. Then I guess they want it to go there. Okay, great. So that's going up to the borders of the presented xy plane, which is what you want. Of course, with the ruler in real life, an actual ruler on the page, it would be better. And of course, also it would be better if the 2 points were further apart. Okay, for 2x add 1, this is real simple. For 2x, okay, first, let's just think about, okay, how do I get out of ruler mode? There. F of x equals x. What's that going to look like? It'll consist of the points 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. And when you plot those, that'll be like a perfect diagonal. Okay? A perfect diagonal. Like that. 45 degrees, bottom left to top right, passing straight through the origin. Exactly. What about f of x equals 2x? The number in front of the x is the gradient. It's how steep the graph is. So let's do it. It's real tempting to say that it's like twice as steep, but what does that really mean? Don't say that, just say it's steeper. Just say it's steeper than this, but it still passes through 0, 0. Why? Because input 0, and that's what you get. Okay, so this will look like that. Now what we want is we want f of x equals 2x add 1. So it's just going to be a modification of that green line right there. In fact, it'll be all of these points bumped up and elevated upwards by 1. So like the line is going to be translated, shifted rigidly upwards by 1, like this. Okay, so I'll do that now. There. Is that right? No, that's not right. Goodness me. Wake up. Okay, so I know why I made that mistake as well. Okay, I meant to do something like this. Right. That's what it'll actually look like. But how could you get that yourself? What if you forget all of this knowledge during exam time or whatever? Just stick into two numbers and then you get 2 points, and then just get your ruler and connect those 2 points. Simple. But here I wanted to give you a bit of an insight into how this is connected to other functions. All right. So I would have stuck in, personally, my 2 favorites. I just stick in 0 and I stick in 1. And I just see what happens. So if I stick in 0, 2 times 0 add 1, that's 1. And if I stick in 1, 2 times 1 add 1, that's 3. And so there are my 2 points that completely pin down the line that I want. Okay, and that finishes that problem set. Great. Let's move on now to continuous relations. Don't know what this is. Gonna have a look. Each graph represents a relation. Determine if the relation is a function. All right, so earlier on, I said that a function can't, you can't have more than 2 outputs for 1 input, right? Like if you have your function machine and I stick in the number 3, I better not hear, 7 or 11. What do you mean? It has to give me just exactly 1 output. 1 output. Okay, that's what a function really is. So the first one is, that's perfectly fine. That's clearly a function. Yes. In fact, that's a linear function. A linear function. Do you see how the word linear has line in it? It's good, isn't it? This is a linear function. What about the next one? What about this one here? This is a function as well. This is a function as well. But wait, I don't see that 6 has anything that's mapped to it. Doesn't matter. Doesn't matter. All that matters is that nothing is that when I have my line of inputs, which is what x is, I don't get like 2 values. Okay, so there's something called the vertical line test. Vertical line test. So on a graph of a function, a supposed function, if I do this, if I plant a vertical line and it passes through a pair of points, it's not a function, because that would mean that I have 2 outputs for a given input. That's called the vertical line test. So, using that knowledge, check out this. This is not a function. It fails the vertical line test. Right there. That's an example of a point of failure of it. So, oh, beg your pardon. Wait, did I say that that was? Yes, it's a function. It looks like an upside down absolute value function of some kind, linear absolute value function, but I don't know for sure until I actually see the whole thing and I see the definition of the function. So this here is no, not a function. It looks like a parabola, but if I really wanted to justify what I'm saying, I would say as -1 has 2 outputs. And what are the 2 outputs? They are -3 right there and 5 right there, which kicks it out of the function club, which means which is not allowed. Real simple, this one not allowed as well. That's a pretty bad vertical line that I just did. It has to be a vertical line, and I really do mean vertical as in parallel to the y-axis. But here you can see that it fails. Similar reason, right? I don't have to write it down, but you already know now how you can justify it. What about this one here? So, on the one hand, seems to pass the vertical line test just fine. But on the other hand, what happens when I input -7? So I just get no output at all? Is that allowed? Depends, doesn't it? Depends on the domain of the function. What if they restrict it to any inputs between -6 and +7? So we'll check out and see what they say. Okay, so the in-house style is something like this. When they show you a full, like a portion of the xy plane there, when they have x going from -8 to +8, what they're saying is that like the domain of this relation is every single number from -8 to +8. And for a function, you have to be what's called left total. So that means every single number from -8 to +8 has to have 1 output. Not 0, not 2, not 3, 1. And therefore, going by their house style, this is not a function. Okay, armed with that knowledge, we can proceed forward. This is clearly not a function. Vertical line test. We see a failure right there. Oh. There and there. Not allowed. An input having two outputs. Not allowed. Okay. Different instructions. Each graph represents a relation. Determine if the relation is a function. Then find the domain and range. This here is very much not a function. It's, I mean, if I input 5, what's my output? This? What's this? So it's not a function, but do they want me to try my best to get the domain and range? Because if I were to do that, I guess I would say that the domain is literally just 5. And the range... So as a relation, when you're talking about relations, a lot more is permitted. Okay, as a relation, the domain is 5. Literally, it's just the set containing the single number 5, and set with one element in it is called a singleton. Quite a cute name, isn't it? Okay, what's the range? What's the range of the relation? Well, the range is every number from -4 to 6, but not including the endpoints. And how do we express that? We say x, and then do a little colon there like that, and then put -6. Oh, beg your pardon. -4. And sort of like sandwich it between -4 and 6, you know? And the way to read this out is x, the set of all x such that x is greater than -4 and less than 6. That's the official way to read it out. But let's check what they say about this, shall we? Good. Not a function. There's the domain. Okay, so they've chosen the XY style. Perfectly valid. Many ways to write things and express things in maths. Actually, do you know what? I actually quite like it that we've got a bit of flexibility in notation. You know, I don't think like any notation is intrinsically superior or whatever, but I do recognize that there is such a thing as house style. You're not going to use notation that's deliberately different to the people that you're working with, because that just creates friction. It slows things down. It's not what you want, right? So just learn how people do it locally, you know? So anyway, is this a function? Absolutely, yes. What's the domain? Well, the domain is every number from -8 to 8, as far as I can see. But maybe they want me to say it's the whole of the real number line, in which case I write R with a bar like that. But if I really want to, I can just say, like, I'll use their style. There, like that. That appears to work. Range. Okay. It's everything from -2 to... I don't know what that is. -1.8. Maybe I could actually work it out. Why not? Okay, I know what it is. It's -2 2/3. So I'll say, no, it's 1 2/3, beg your pardon. So -2. How about that? Okay, all real numbers, which you can indicate using that fancy R there, like that. Y is greater than or equal to -2. I guess that's true. That's implied by the just assuming things about the function, how it looks over there on the left and how it looks over there on the right. Okay, we assume that it just carries on going upwards. But from what I can see, it's from -2 to 1 2/3. I'm just going to go by what I can see. I'm not going to make assumptions, not too many at least. All right. Here, is this a function? Yes. In fact, it's a quadratic function. It looks like a quadratic function. It looks like a parabola. But did you know, I guess I don't have anything here. Did you know that if you sort of like hang a string like that, this is not actually a parabola? It's something, that kind of curve is called a catenary curve. Anyhow, so right, so we have to say what the domain is. Okay, so according to them, their way of doing it is to just say that, assume that it's the whole of the real numbers. Okay, what's the range? Well, the range then for a quadratic is that it would just keep on going up like that. And so we say that y is anything greater than or equal to -3. Great. What is this function here? Beg your pardon. I just called it a function already. I don't know if it's a function. And clearly it's not, because of the fail there. It's not a function unless you restrict the domain somehow. You could do that. But as it stands, it's not a function, right? So what is the domain of this relation? The domain is any number that's less than 5. Why not 5 itself? Well, because this is hollow. That means that you have no output here. So 5 is not an accepted input because you have no output. Okay, well, what about the range? Well, going by their assumptions, that's going to be -5 and up. Oh, and include the -5 for me. There you go. Problem 11, we have a circle, and a circle is not a function. Sorry, it's just not. You can have a semicircle, though. That's fine. You can do that. In fact, you have to kind of like glue a pair of functions together to get the whole circle. Okay, so what's the domain? The domain appears to be any number from -3 to 3, inclusive. What's the range? In this case, the range appears to be any number from -1 to 5, inclusive. Okay. Bonus knowledge. What's the center of this circle? The center of the circle is 0,2. So and what's the radius of the circle? Well, the radius is 3. And the general form of a circle is like this. So I can actually create the equation of this circle, and it's going to look like this. Sticking in 0 in the A spot, sticking in 2 in the B spot, and sticking in 3 in the R spot. So 9 there like that. And then you can sort of expand it out to get x squared and y squared. Take 4y and then plus 4, and then take away a 9 from both sides, so -5 equals 0. And that there is a circle in disguise. It's a circle in disguise. So anyway, what about this what about this relation here? It's not a function. Why? Because 8 is not included. And what is the domain? The domain appears to be everything from -7 to 7. Oops. I should just write 7 there. And what is the range? Well, the range appears to be everything from -6 to 4. Great. All right, so that was basically all handled, and that's all I plan to do this session. Okay, so thank you for coming or seeing, and I'll see you soon. Bye-bye.